As you all know, we have started studying fifth lesson of your syllabus, that is electrochemistry. Before starting today's session, we will just revise what we learned in the previous session. In the previous session, we learned about a reference electrode. What is then reference electron means? It is an electrode whose potential is arbitrarily taken as zero or is exactly known. And the reference electrode we studied is standard hydrogen electrode. We call it SHE. She. This SHE is the only electrode or only reference electrode included in our syllabus. So it is very important as far as exam is concerned. We learn about the construction of SHE, its formulation, the reactions taking place, as well as the applications and difficulties in setting up SHE. We know that the reference electrodes are used to determine the standard potentials of other electrodes because SHE can be used as cathode as well as anode, and if it is connected to another single electrode, and if we measure the cell potential, the total cell potential belongs to that another electrode which is connected to SHE because the potential of SHE is zero. Hence, it has this great application to measure the EMF of a single electrode. There are many difficulties in setting of SHE because to get electrode of 0 volt, it is necessary to maintain some conditions, and those conditions are the difficulties in setting up SHE. The conditions are like we have to use pure and dry hydrogen gas. The pressure of hydrogen gas should be maintained exactly at 1 atmosphere, and the concentration of H plus ions should be 1 molar. Then only we get 0 voltage. And if we are unable to maintain the conditions, then we can also calculate EMF by using Nernst equation. That also we learned in the previous session. So that is all about SH. Now, actual galvanic cells we are going to study, which are included in your syllabus. So in today's session, we are going to learn about the galvanic cells useful in our day-to-day life. So, the galvanic cells, we also call them voltaic cells, are in common use, and they are mainly classified into two types. The first is a primary voltaic cells and another is secondary voltaic cells. So we'll start with the first type, that is a primary voltaic cells. When a galvanic cell discharges during current generation, the chemicals are consumed. That means when we use galvanic cell actually, then the reaction gives us current. But during this current generation, the chemicals are consumed or used. In primary voltaic cells, particularly, once the chemicals are completely consumed, then the cell reaction stops. And as the cell reaction stops, we cannot reverse that cell reaction. Even after reversing the direction of current flow. That means, in short, we can say these cells cannot be recharged. Once consumed, once used, we just have to throw them. Because once used, the chemicals are finished. When the chemicals are consumed, the reaction stops and we don't get current. Hence, the primary voltaic cells are the cells which cannot be recharged. The best example is a dry cell. Dry cell batteries we use in our day-to-day life for laptops, for remote controls, toys, etc. Those dry cell batteries, when we use, we just have to throw them. We cannot reuse them. These are primary voltaic cells. Now, what are secondary voltaic cells then? The voltaic cells which can be recharged are called secondary voltaic cells. That means those cannot be recharged are primary and those can be recharged are secondary voltaic cells. That is the main difference between these two types. How these cells can be recharged? For that, in these cells, the chemicals consumed during current generation, those are regenerated. And for that purpose, an external potential slightly greater than the cell potential is applied across the electrodes. Because for current generation, as you know, we require chemicals. Then only the redox reaction will take place and that redox reaction will give you electricity. Hence, during discharging, the chemicals are consumed. And after complete usage of those chemicals, the reaction stops. But in secondary voltaic cells, those chemicals are regenerated by recharging. And for that, we have to apply an external potential. And that external potential should be slightly greater than the cell potential we obtain by using the voltaic cells. This results in a reversal of the direction of current flow, causing the reversal of cell reaction. And when we apply the potential, what happens? The direction of current flow reverses because of the reverse or reversal of cell reaction. Understood? We will take an example afterwards. We are going to see in detail about the secondary voltaic cells as well as primary voltaic cells. Just now understand that we can recharge secondary voltaic cells by applying potential. So, it is amazing to see that secondary cells are galvanic cells during discharge and electrolytic cells during recharge. Understood? During discharge, that means during usage, when we use that cell, that is galvanic cell, because only galvanic cell gives us electricity. But it becomes electrolytic cell during recharge. When we apply a potential across the electrodes, that cell becomes electrolytic cell. How it is possible? What is the difference between these two types? As we know, voltaic cells are the cells which gives us electricity by using chemicals. That means in galvanic cells, chemical energy is converted into electrical energy. But in electrolytic cells, electrical energy or electricity is used to carry out a chemical reaction. That means electrical energy is converted into chemical energy. Exactly opposite. But in secondary voltaic cells, during discharging, the cell is galvanic cell, and during recharging, cell becomes electrolytic cells. In galvanic cells and electrolytic cells, there is one more difference, a major difference, that in galvanic cells, anode is negative and cathode is positive, while electrolytic cells have anode positive and cathode negative. But at anode, there is oxidation. At cathode, there is reduction. That is the definition of anode and cathode. So, at anode, there is always oxidation, and at cathode, there is always reduction. Still, in galvanic cells, anode is negative. In electrolytic cells, anode is positive. While in galvanic cells, cathode is positive, and in electrolytic cells, cathode is negative. But how this happens, we are going to see in detail when we learn about the secondary voltaic cells by taking an example. Now, what are the examples of secondary cells? Those are lead storage battery, mercury cell, and nickel cadmium cell. Do you know lead storage battery? The battery we use in our vehicles. That is, the battery used in automobiles, where the battery gets, we say that while running of vehicle, the battery is used, that it discharges, while at rest or we can recharge that battery and we can reuse that. So, lead storage battery is the battery we use in automobiles. There is one more example I can give you which you use in day to day life, and that is inverters. In our house, we use inverters. What are inverters? They are a discharge or they give us electricity when we use them, and they get recharged while at rest. Hence, the one which can be recharged is called secondary voltaic cell. Understood? So, this is all about the types of galvanic cells we use in day to day life. We are going to see the examples of each type. The first type, that is primary voltaic cells, the example we are going to learn about are is dry cell. So, this is primary voltaic cell. We call it Leclanche cell. Now, the name suggests that it is a dry cell. The cell is without liquid component, but it is not completely dry. But it contains a viscous aqueous paste. Because if we use completely dry chemicals, then the movement of electrons is not possible. For movement of electrons from anode to cathode, we require a medium, and that should be liquid. But dry cell, the battery we use, is not completely dry. Instead, we use a viscous aqueous paste so that it is easy to carry dry cell, but it still gives us reaction, and that gives us electricity. So, this is the first example of primary voltaic cell. So, we will see in detail about this. The first and important thing is construction. So, we will see the construction of the cell. In construction, the important points, always remember this, are what is anode, what is cathode, and what is the electrolyte used. These three are the important things which are required to carry out a cell reaction so that it generates electricity. So, in construction, we'll see that the container of the cell itself is made up of zinc and which serves as anode. The container of dry cell is made up of zinc. This container has a inner lining. The container is lined from inside by using a porous paper. This porous paper separates anode and cathode, or separates anode from the other material, the paste we are going to use, everything from anode. So, anode and cathode and the electrolyte are separated by using a porous paper which is lined from inside of the container. It is also called paper spacer. An inert graphite rod. We are going to use a graphite rod, that is carbon rod, at the center of that container, which is immersed or dipped in the electrolyte paste, which serves as cathode. So, understood about anode and cathode? Anode is zinc container, cathode is a carbon or graphite rod, which is at the center. These two anodes and cathodes are separated by electrolyte. So, here is the figure. The container of the cell is a zinc container, so it carries a negative charge. At the center of the container, this black colored is graphite rod, which is cathode, hence positively charged. There is a paper spacer from inside of the container which separates anode, cathode, and electrolyte. Immediately surrounding the graphite rod, there is a paste of manganese dioxide and carbon. Immediately around the center graphite rod, there is a paste of MnO2 and carbon. And the remaining part between the cathode and anode, we can say paper spacer, is filled with paste of ammonium chloride and zinc chloride. Ammonium chloride and zinc chloride. And this paste is thickened by using some starch so that the paste becomes somewhat thick and hence leakage is controlled. The upper part of the container is sealed. There is a brass cap given at the upper end of the graphite rod, which is open, which is better for connection. Hence, positively charged cathode and negatively charged anode is separated. So, this is all about construction. We will just revise all the points again. The central cathode is surrounded by a paste of MnO2 and carbon black. The rest of the cell is filled with an electrolyte. Which is that electrolyte? It is a moist paste of ammonium chloride and zinc chloride. You have to remember all these things. Some starch is added to the paste to make it thick so that it cannot be leaked out. The upper end, the cell, is sealed at the top to prevent drying of the paste by evaporation of moisture. So that upper end is covered just to avoid the drying of the paste, because the paste should be moist always. Hence, the upper end is sealed. So this is all about the construction of the cell. The cell, you have to draw the figure of the cell in the exam. So better to practice the cell. We were going to end today's session here because the cell reactions are a bit complicated, hence it will take some more time. So in the next session, we will learn about the cell reactions occurring at anode and cathode, as well as the net cell reaction and uses of a dry cell. So this is all about today's session, and time for assignment now. The question is simple, just you have to define primary voltaic cell and secondary voltaic cell. Give their examples as well. Thank you.